Hello everybody, my name is Daniel Whitman,
My name is Jacob Smith.
and today we're presenting on a senior project titled ORMR, the modular snake robot, under our advisor, Dr. Z.
So first we want to talk a little bit about our final design. We have our CAD models up top and what we have constructed this semester on the bottom. We have had a lot of fun and we've learned a lot throughout the past 2 years working on this project.
So first, a little background introduction to what our project's going to be doing. So we all know the mining used to be a fundamental part of the infrastructure here, especially the Luzerne area, but it's since faded away somewhere around 1960, 1959. But when it faded away, it didn't just disappear forever. It left little traces of itself in the form of abandoned mines. But what's the big deal, right? It's gone, we're not using them anymore. Well, these abandoned mines, they have a lot of pollutants and minerals in them. And what happens is water enters these abandoned mines, and then it gathers all these pollutants and deposits into things such as the Susquehanna River, as you can see at that image. We took that from Google Earth, just upstream of Wilkes-Barre. You could see all the iron deposition going in the Susquehanna River, causing it's very polluted. So the important thing is how the water is getting into these mines to gather all that pollution, and that's what our project is going to really focus on.
So what is our purpose? Our purpose was to design some type of robot that can travel into these fractures and map the geometry so we could retrieve the information for analysis on how the water is traveling into the mines. On the screen now is our first prototype that we created last year. It was functional, but there was a lot of electrical tape and electrical problems that we ran into, and it needed much improvement. So some requirements that we gave ourselves for this new model was we wanted a new compact design that would make it easy to fit through the surface fractures, but we also wanted it to be lightweight because the lighter it is, the less energy we have to use to move it, which helps us with making it internally powered. We want wireless communication, we want this thing completely wireless, because once we're navigating through these fractures, we don't want a wire getting caught and we lose connection with the robot. We would also like to make the robot durable and maneuverable, but we would also like to make it modular so we can adapt to certain situations. So, on the screen, I have a picture of one of the surface fractures that Dr. Whitman took us to, located in Nanticoke. I have my phone in the image for reference. These surface fractures average around 2 inches in opening, and my phone is there for reference.
So how are we going to meet these requirements? For our design, we managed to get a very narrow robot. So as you can see by this figure, it's a bottom-down view of one of the segments we're using. The width is 1.75 inches, and then the diagonal is 1.9 inches. So in theory, it should be able to easily fit within one of these larger fractures. For the length, it's about 38 inches, just over 3 feet when it has all the segments. So that should allow it to wrap around things if it needs to climb, and it also should be not too long so it won't get tangled while it's moving. For the weight, it's about 2.2 pounds, so one of the motors can move about half the robot very easily, so with all 12 motors, it's very maneuverable. For self-containment, each segment, as I'll show later, has an individual battery, and these batteries will work together to help power the robot. For communication, we're going to use radio, although that might change depending on how it works in the surface fractures. And then for adaptability, we're using a material called Markforged Onyx that Dr. Moon gave us. According to them, their data sheet, it's about 1.4 times stronger than regular ABS, so it's very durable. For movement, each motor gives it an individual degree of freedom. So with all 12 motors, we have 12 degrees of freedom, so it's a very maneuverable robot. And then finally, we created a modular design, as I'll demonstrate later, so we can actually change the length to fit our specific need.
So our work breakdown structure, we really wanted to focus all our attention on 3 main parts, which would be our mechanical design, our electrical design, and our software design. For our mechanical design, we really wanted to get a nice physical design down with all our components that we need. We wanted the whole thing laid out. For our electrical design, we really wanted to focus on the circuitry and all the sensors that we would need to gather our information. And for our software design, our main focus was on the motion of the robot itself.
So here's a little week-by-week schedule that we put forward to ourselves for these 2 semesters. As you see right now, we're in our final fall presentation, and looking over here, we should be completing construction. So we're a little ahead on schedule, and then moving into next semester, it will be testing and improvement. Whoops.
So thanks to Dr. Zhu, we were able to get a Type 1 grant for this project. We didn't have to work with the $500 budget that most senior projects got. In total, our project that we created this semester came out to about $3,400. But if we were to have this in the marketplace, we decided that it would approximately be about $5,000 per unit.
So now to the important part, we're going to talk about the design. So as you can see here, we've got our CAD model and our completed picture, as you saw in the beginning. Now the robot is split into three main parts. You have the tail, which is at the bottom, segments in the middle, and the head's at the top. So to start with the segment design, there's two main pieces. You have the back here, and then the cover. So the back is what the servo motor fits in and where the battery fits in. And then the cover goes over top to protect everything. Down here, we have an image of one of the segments with the cover taken off. So as you can see, right there, that's the battery. There's a cavity where it can fit its plug. And then up there, you can see how the servo motor slides in. And to make it modular, as you can see here, all the wires have plugs on the end. So what we can do is the segments plug together rather than being hardwired together. So if we need to change the length, all you have to do is either plug a new segment in or unplug a different segment so you can have as many degrees of freedom as you need. Oh, wrong button. So for the tail, you can see it's very similar to the segment, right? You got the servo motor on top, and then there's a battery in there. And then underneath, that's where we fit the electronics and the circuit board, which I'll show on the next slide. And finally, for the head, it's got its own circuit board, and then the top, we call them the head tips. They're removable and interchangeable. So these head tips are where we're going to put the specialized sensors. So for example, this one has laser distance sensors. Another one, as we'll show up here, just has an LED. And in theory, we're going to have one with the camera. Now for the electrical design, we have our two PCBs and then the circuits below. Start with the head. The main function is to gather data from the sensors and take information from the controller. The two main sensors on the board are an IMU and a magnetometer, and it can combine that data to find out 3D orientation of the head in real time. And then for the tail, its main function is to control the power of the servos and to control the position. So it can choose between using battery power or external power, using these two transistor circuits, and then it measures through a shunt resistor the current, and it can limit that to control the strength of the robot if we need it to be more adaptable.
So once again, we have our controller on the screen. We have the CAD file up top and the constructed controller on the bottom. Our controller's main function is just to control the robot entirely. The joysticks are for movement. The buttons are for different loads. We have a display to give us all our sensor information, and we have LEDs for a better indication if something goes wrong. So the whole purpose of our product is to go into these fractures and find out the geometry and how this water is traveling into the mines. This is going to help us with the pollution control going into the Susquehanna. We also plan in the future, hopefully, putting our robot into search and rescue situations where we can put the robot in a situation that it would be deemed dangerous for a human life to be in, which helps us hold paramount the safety and health and welfare of the public from the NSPE Code of Ethic 1.1.
So moving forward in the next semester, we constructed a 4-phase testing plan, as you can see on the board. Phase 1 is just component testing, so that's testing each individual part and as well as the total assembly to see if it functions properly. Phase 2 would be to get basic movements, so that's moving forward and backwards and side to side. Phase 3 is difficult terrain, so that's taking the project outdoors and seeing how it operates there. And Phase 4, we came up with the name the Mount Whitman test. And we're going to put a little animation on the screen, but no, this animation is not entirely accurate to what the test is going to be. But to start, we're going to need a John Deere front-end loader like that. Next up, of course, you need a responsible operator for safety. Then, we're going to load as many cinder blocks as physically possible into that front-end bucket. They get dumped out, as shown by this animation. Once they're dumped out, they're going to fall and break and crumble into a big pile. And the important part about this pile is that we don't know the geometry of the pile. So it most mimics the surface fractures where we don't understand how, what they look like. And then finally, we're going to have our accurate representation of our robot come in an attempt to maneuver over or through this unknown geometry.
So for next semester, we really want to get reliable movements down so we can execute our testing program. And if any hiccups come up in the software or we see room for improvement, we'll have to do the software improvements. And right now we have a functional camera on order. The camera is going to help us capture that video and images of inside these fractures. If we get caught in like a tight situation where we can't move the robot any farther in, we plan on using the camera as a pan, tilt, and zoom type feature to gather more information. And if all goes well with our testing, we plan on trying to attempt getting into these fractures.
So that's enough about the talking. I bet you all have one important question. You have this, this design, and that's great, but does the robot work? And our answer is, we really hope so. We did about an hour ago, so we'll see now. But to start, before we get there, this is our first prototype we made in 2021. As you can see, it's got very long wires, and it's not great with the connections, so we get damaged easily in the fractures. This is the controller we made for it. It's a true marvel of engineering with lots of electrical tape, as all good things should be. And this is our new controller, which I'm pretty clumsy, so I actually dropped it about 10 seconds before the presentation. But it would not be pieces like that. For our modular, like I said, they're all put together with plugs. So we actually took 2 of the segments out like that, and you can see that the robot is still functioning now. So we're going to put on a little demonstration. Hopefully it doesn't blow up. Hopefully it doesn't break. And we'll see what happens. Makes a fun little cute sound. That's part of the